we're like, okay, that'd be really useful.
Accessibility.
Yeah.
It's really useful for finding unexploded work.
Yeah. You guys, anything else? Anybody got anything else?
Reposits.
Yeah. Actually, minerals is a big thing. Okay, so that's numero uno. And the amazing thing about this is that there's, as far as the source goes, the Earth provides. What? Arnold.
Seismic.
We did seismic, yes. And what was the things that we were able to find, especially things that might be of interest to you guys?
Depended on the velocity of waves. So the voltage.
Well, we had there were a number of elastic properties, right? So there was, there's sort of density, and then there's BP and BS and things like that, right? So how fast things travel. From your perspective, maybe one of the things was actually to figure out, okay, so geological engineers, you want to find, what the thickness of the bedrock is. Where's my stable area on which to build something, right? And then we found that, we're actually able to have refracted waves, and so we're actually so we can get thickness of layers or the dips of layers. We could do it that way. So this was seismic refraction. What was the other thing that we did with seismic? I heard it, yeah, reflection. And here, what we're doing is looking for waves that are kind of bouncing back, right? So we're actually able to get identification of units here. What was the thing that was important in describing whether something got reflected or not? Stefan?
The acoustic impedance.
That's right. So the acoustic impedance, which was the product of the density and the beam wave velocity. If that changes, then we get a reflection coefficient for the P waves. We could also have a reflection coefficient for the S waves. A different one. So each different kind of wave would have its own reflection coefficient. So that was pretty good. And then there was a third component of this, which we didn't talk about maybe a huge amount, was something called MASW. And what technique is that used for? And actually, what is that technique? Anybody? Do none of you guys at the back have a card? I'm going to ask you. Your name is? Natalie. Okay. Try to remember, but you need a card. Okay, Natalie. What's MASW? Right. And what kind of waves did it use? Surface waves, right. So these guys here, these guys are all kind of body waves that are going down, but MASW, these had surface waves. And in that very first lecture or example that we talked about, they were just kind of like dropping a weight down here on the ground, and then they'd be measuring these waves as they come through. And then you have to do some processing, but eventually you get stuff that's related to shear function. So that's kind of cool. Gives you some idea about maybe thicknesses of layers or something like that. Then the last one that we did, what was the last guy? What did you just do? Quentin?
GPR.
We did GPR, which stands for?
Ground penetrating radar.
Ground penetrating radar. And it was sensitive to which physical property?
Conductivity and electric.
Right. So primarily the idea with GPR is that it's associated with the electrical permittivity, or sometimes it's called the dielectric constant. And dielectric constant varies between, sorry? 70. Sorry? Well, yeah, that's the numbers for 180. That's a good start. So your name is Lucas? Okay, so what is GPR kind of fundamentally connected with? Yeah, that's true. We can go one level even farther down. So the person who's sitting next to you. Okay, we'll keep going. Why? Well, at least give me your name. You guys got it in your cards. Please do that. Okay? How's that? Oh, sweet. Okay, and then your which property? Yeah. Yeah. And what is it really depending on? Right. And do you understand kind of what that is? Anybody?
Doesn't it depend on the amount of water? It depends on whether material is.
How strong something is polarized.
How strong something can be polarized. That's the issue. And what do we mean about what's the deal with polarizing something? Yeah?
So a polar molecule would have like a positive and a negative sort of like region on it.
Right?
Negative end, and then so it's polarized and aligning with.
Perfect. Oh, can we give her a star? That's a perfect. Even if you, I'm not sure I should give you one if you don't have a. You have a card? Yes, thank you. Okay, so look at this guy here, right? Okay, well, and this is not totally unrelated to where we're going to go today. So, if I take something like this, okay, I can kind of think of it as like a dipole, right? Where I got kind of a minus and a kind of plus, right? So this is kind of like a minus, and that's kind of a plus. So that kind of gives rise to something that looks like that. Okay? Okay, suppose I have an electric field. Okay, and I'm going to put on that. So I can talk about electric field, a nice big thing here. E. What is an electric field? Up the back, second at the end, and left here.
Field generated by
By an electric what?
Correct.
Pretty close. Anybody else? Yeah.
Is it caused by electromagnetic waves?
Right. You can go even more simple. I mean, remember we talked about in magnetics, we talked about kind of like a magnetic charge, right? So we said, oh, we got a plus charge. Then what does it do? It radiates out a magnetic field, okay? So it gave us, a magnetic field that emanated out from that, right? That was a magnetic charge. That's a magnetic field, okay? How about an electric field? Same. I could have a charge of plus Q, so many coulombs, right? And I'm going to get an electric field that comes out here. So the direction of my field kind of, it's all kind of controlled by, let's say, these charges. Yeah. So now, when Sagi was talking about electrical permittivity, talked about dipoles, and we talked about electric fields. Can we somehow put all of that together in here to sort of think about, okay, what's going to happen? Let's suppose I just take this guy. So suppose I have something like that. That kind of looks like a dipole, right? Just the same as we did with in magnetics. We had like a north, which was positive, a south, which was negative. And we had fields that kind of came up like that. So that was our dipole. Well, we got the same thing here, right? This is a dipole. Here's plus, here's minus, right? So I've got to think about this as an electric field. Those feel like this. And now suppose I put an electric field on here. I'm going to tell you that the electric field is pointing in that direction. What's going to happen to this molecule? Go ahead.
It will align with the field.
It'll align, but which way is it going to do that?
Positive to right, negative to left.
Right. Good question. Why is that? He's right. So, your name? Abbas? Why is that? Well, I think you first of all can choose to agree or disagree. But right behind? Yep, you.
I'm not sure.
Anybody? Thank you. So remember, if I've got a positive charge here and I have another positive charge, what's it going to do? It's going to go up this way, right? If I have a negative charge, it's going to be this way. Okay, so now I'm telling you I've got an electric field here. It's pointing in this direction. This guy's going to turn, and he's going to turn. So it's going like this, right? Because we're going to make an electric field. Here's how to think about it. An electric field is pointing in that positive direction. You can just think about like this super big charge here, big positive charge. That's going to generate an electric field out like that. Now it's going to see this. That's going to go like that because opposite charges attract, and it's going to go. Okay, so that's the fundamentals of kind of electric fields and dipolar molecules. When we talk about electrical permittivity, we're actually talking about how easy it is to move this thing back and forth. So if I have an electric field that is going this way, then the molecule is going to come like that. But it might take some time, right? Because there's other molecules or ions around. And then if I change that electric field to make it look like this, okay, can it actually go back and sort of flip directions? So electrical permittivity is somehow associated with the ability to polarize molecules and the sort of the ease with which that. So that's really useful in all kinds of things. We saw it for, well, what are some good examples? Where is GPR useful? Yep, in the white sweater. Where's GPR useful?
For the type of goods that just awesome.
Yeah.
Looking for varied objects.
Yeah, some kind of varied objects. Anything particular?
Pipes.
Yeah, pipes are great. Thickness of glaciers or something. That's fine. Okay, so yeah, there's a lot of infrastructure, right? Yeah, ice thickness, some kind of landfill stuff, all kind of works for GPR. Now, the one thing that Sagi talked about, and it kind of came into play a little bit later, somebody actually mentioned it, that the physical properties that were associated with was electrical permittivity. That's really that's the GPR fundamental. But at the frequencies that we're dealing with, there's also something called electrical conductivity. And electrical conductivity is kind of the bane of GPR because this causes a lot of attenuation. So if you're trying to pump GPR signal into seawater, you ain't going to get very far. So we found out that the electrical conductivity really attenuated the signals. It could also give rise to a reflection. So that's why it works if you're trying to find a metal wire. The great thing about GPR is you can find a plastic pipe which has no, no conductivity at all, right? So you can find a plastic pipe because now you've got a difference in electrical permittivity. But you could find a metal pipe because it's going to have a reflection coefficient. So there's a couple of things going on. But this property here plays a role. And actually, I want to start to talk about this. Within the context of geophysics, if you look at the spectrum of problems here as a function of frequency, so imagine you've got some kind of a harmonic wave that is going on. So as a function of frequency, you can get some really high stuff out here. So here's GPR, and this might be, 10 to the 7th to 10 to the 9th hertz. There's a whole range of surveys, and we're going to do those. Those are called electromagnetic surveys that kind of span this intermediate range here of maybe 10 to the -2 to maybe 10 to the 5th hertz. So that's a big area. And that's called the EM. And when Sagi was talking about diffusion, maybe we've used that word a few times, diffusion, and that had that skin depth. So in the diffusion, the skin depth was 500 root rho upon F. So when things are governed by this, that's sort of this diffusion stuff in here. The electromagnetic signals don't really propagate as the way they kind of go, they just sort of get barreling in a waveguide. So it's going to be that. What we're going to do today is actually go all the way here to frequency equal to 0. This spans a whole new set of surveys, probably from the point of view of the geotechnical industry, maybe the most important survey that you do, and it's called DC resistivity. So that is where we're going to go. So I want to tell you about how many people have been involved with the DC resistivity experiment? Yeah, under what conditions?
During mineral exploration.
Okay. Anybody else? It's used a lot. Like this is like one of the mainstays for geophysics, for Golder, or especially for geotechnical problems. They'll do where they're doing all the LNG prospective areas for siting the plants. They go through. They just blanket the whole area with DC resistivity. So I'm going to talk about DC resistivity within the context of our usual framework here. Talk about physical properties and basic principles. So first of all, we have the introduction. Whoops, where did it go? Where did that go? Just a second. So if you go to the GPG, then there's something called DC resistivity, and
It's not showing up. I think you probably do. Close it accidentally.
oh, okay, all right, never mind. If you go to the GPG, you can see what's happening. Otherwise, I thought I would actually be able to, because I can see it here, but
Yeah,
it doesn't mean you can see it. So here's our electrical resistivity or the electrical conductivity. Remember from your first lab that you did, you saw that those were the reciprocals of each other. I think we've also seen this, but it's sort of an indication of what the range is of electrical conductivities or resistivities from a whole bunch of different rocks. In everything that I do, in fact, that virtually all geophysicists, we tend to use the two words conductivity and resistivity almost interchangeably. And it kind of depends upon whether you're talking about a number that's in the order of 1 or much different. For this particular case, I'm going to try to talk as much as possible about resistivities. So as you saw again in that first lab, the resistivity told you something about how easily current could pass through. And you had some very resistive rocks, units of ohm meters. So this is like 100,000 ohm meters, igneous, metamorphic rocks, permafrost, things like that. But you could also have rocks that had very low resistivity, like massive sulfides or salt water. So here's the basic DC resistivity experiment. It is probably the, aside from magnetics, it's probably the oldest geophysical experiment that is around. And part of that is because it's really simple. We're going to see this guy a fair bit. So this is actually a representation of a mineral deposit in Australia. It's called the Allura deposit. And there's a number of elements here. The first is that there's an overburden, which is actually 12 ohm meters, so it's fairly low resistivity. There's a host rock, ground, 200 ohm meters. There's something called a Gaussian. That means anything to people. Anyway, it's a kind of a cap on this, and that's quite resistant. And then down below here, we've got a mineralized system, but it's in 2 units. The outer region is quite less resistant than here, but the inner portion here is a very low resistance. So what's the experiment? Well, the first thing we're going to take a generator or a battery, and we're just going to hook 2 electrodes up to it, and we're just going to pump those into the ground. So we're going to have a current that's going in here, so it's hooked up to a generator, current that's going in, and a current that's going out here. So it's a positive and a negative. Now, when we put those currents in, you can imagine that the path of the currents is going to depend upon the body that's here. So if it's a very resistive body, the currents are going to kind of flow around. If it's a conductive body, currents are preferentially going to flow around. The essential thing that's happening as currents flow through, they're actually going to build up charges that are sitting on the outside of these boundaries. And then each of those charges is actually going to be associated with with an electric potential that we see. So what we were talking about here was electric field, but there's any particular charge Q, okay, can have an electric potential V, which is 1 over 4 pi epsilon naught Q upon R. So this has an electric potential out here, and the electric field is just given by the gradient of that potential. So how much it changes as a function. So the bottom line is we get charges, so we can measure voltages that are sitting up at the top. We have a couple of apps, and I think these are exceptionally good tools for really learning and understanding. There's 2, and we'll look at them today. There's one for a layered earth. So now what you're seeing here is you're going to put a current electrode in here at A, and then we're going to watch how the currents flow through the earth, and we're going to measure the electric potentials of the surface. Then there's another one with a buried body in it. It's actually a cylinder, and again we'll explore how the currents, charges, how everything. So what's the uses for this? There's a huge number. First of all, minerals, water. Saki showed you that example for in the mine, that mosaic mine in Saskatchewan, where they're looking for potash, and there they're looking for trying to find water that might invade. DC resistivity is the method of choice for doing that. Oil and gas, geotechnical problems. This actually comes from our interaction with people in Switzerland. They're looking at glacial flows, basically landslides that could come from glaciers. And then there's issues, environmental, especially saltwater intrusion. There's two things with respect to water. One is finding the depth of the water table. That's huge. And the other is sometimes discerning whether or not there's salt water coming in. We have an interaction with, actually it's an ex-UBC grad who spent his last year doing humanitarian work in Myanmar, where he first of all built a DC resistivity system, went down, collected some data, and is trying to train people how to use this. And again, the problems there is scarcity of water. And actually, if you're going to make a difference in this world, one of the things that you really can do is find water in really poor countries. First of all, that helps people plan their lives. You need water to drink. But perhaps the more important thing is that typically right now in a lot of these countries, it's the female who is responsible for collecting the water. And in some of these places in Myanmar, the ladies they were on foot 2 hours each way and then carrying water on their heads back. So not only is that huge work, that is taking women out of the workplace and, well, it's putting them into a workplace and it's preventing them from getting, education and doing something useful. So I think from if you're talking about a humanitarian thing and a use for DC resistivity, groundwater is really a big issue. So physical property we've kind of already talked about. It's electrical conductivity. And just to be clear on the units, so first of all, the resistivity is in ohm meters, and electrical conductivity is Siemens per meter. So those are the two units, and one is just the reciprocal. So you're familiar with Ohm's law. Just a second. So here's what you had in grade school. You had a generator, a little battery, had a potential difference associated with it. Hook up a resistor, you get a current, and you have Ohm's law, which said that V is equal to IR, and that R is the resistance of this object. When you talk about physical property, you're talking about the resistivity, which is sort of related to what's kind of happening at a point. The resistance is taking into account all the geometry. And in the first lab, what you did is you measured the resistance, you knew what the area of that cylinder was, you measured the length, so you put them all into here, and you got their resistivity. Okay, so that's what you did. If we look at electrical conductivity or resistivity, I've shown you, it goes over many different orders of magnitude. The reason that things vary, for instance, a particular kind of rock has such a wide spectrum of resistivities, is that the electrical resistivity depends on many, many factors. I'm not sure how well you can see this from the back, but this is like a little chunk of rock, and I don't know, can you see that there's a difference in texture here compared to there? So there's some kind of a line that's going, so you can see that there's a texture difference. There's definitely porosity differences. The main conductor of electricity in a rock is actually the ions that are in the water. And so if you get different porosity and you get different ways in which the fluid pathways are connected, you're going to get different conductivities. And also there's a couple of things. There's the matrix. Clearly the background matrix here is different than it is here. And you might have some metals in here too. So metals will also conduct easily. So there's basically two things. There's sort of metallic conduction, and then there's also fluid pathways. So what are some of the basic principles? Well, let's first of all kind of get through what the governing equations are. We have Ohm's law, that J is equal to sigma E. And then I already said that the electric field is gradient of the potential. If we're actually going to put in a current someplace, then the divergence of that current has to be such that if I have a little block of something here, if there's a current that's in here, then it all has to go out. If there's no current in here, then there's no current, no net current that's flowing out. And that comes out to this relationship. The bottom line here, I think, is that if we do the following, if we put a current into the ground, okay, then we can actually solve for what the electric potential is at any place here. And that electric potential is given by this formula, rho naught I over 2 pi r. So we have a formula that then allows us to relate the electric potential to the resistivity and the current that's going in, and r the distance here. So just to be absolutely clear on this. So here's our Earth, and we've got a resistivity rho, so let's just assume it's a constant. So we put a current in here, so we attach this to some generator. And that current is going to flow outwards through the Earth. At each particular point here, so let's suppose we're at a region distance r, there's going to be an electric potential that is given by that particular formula. So rho is the resistivity, r is the distance from the current electrode to the point, and I is the actual. So I'm just going to flip through and then I'll exit this and we'll go to the app. So what we're seeing here is a current. So this is the horizontal position along this way. And this is the electric potential. If we look to see inside the ground, then, I mean, you can imagine how, well, maybe I've got lines plotted like that. Why are they, why are those lines, well, I should ask if they're intuitive. If I had asked you to plot the currents, what you would have thought, or is there something different? So imagine, maybe I could have started with this. So let's suppose we put a current here, a complete uniform half-space. Then how can that current flow? How is that current going to flow out? So somebody could just tell me what's on the slide, and then we'll ask why. Anybody?
In all directions?
It's going to go, yeah. So there's, I mean, here's the basic thing. There's no preferential direction in which I can go. The current has to go here, but there's nothing different over here than down there or over here. So the current has to be flowing in the same direction. The other is that, if you thought about a little hemisphere here, then if this is the current I that's going in, then you still have to have that same current that's flowing out. And as this thing flows out, you just see the currents now that are just. One other piece of information is that if I put a current into the ground here, okay, that current is just connected to a battery, right? So I've got a generator here, or I've got just a big battery here. positive here, negative here, right? So this battery is just like a charge device, right? So the moment that I hook this thing up to here, okay, it's just as if I just put a big positive charge here. And since we know what the potential is like away from that positive charge, that is actually the thing that tells us that potential is just decaying as this is state here. So that's what happens if I have a single electrode. And so I've got a single electrode here, current, and I've got that V. So if I'm going to plot this, here, if I'm going to plot that, what's going to be the graph? What's that thing going to look like as I go up this way? This is going to be here, so this is going to be R on this way. What's that going to look like? Let's see, who's in the back in the green?
Yeah,
Well, if I'm asking you to plot this thing, B is equal to some constant over R, what's that going to look like?
it'll decrease as R gets.
Good, and what's going to happen as R gets smaller? Pardon me?
It'll increase.
Yep, and to how big?
To just.
Infinity, exactly, yeah. So if I kind of charge here, then the electric potential is actually infinite, and then falls off as 1 upon R. Okay, yep.
Just before you go to theory, can you explain what a uniform half space is?
Oh, yeah, a uniform half space is a half space. Do you know what half space is? Okay, everything here is like a whole space, right? Okay, that's everything, okay? So a half space is half of that. So it's like taking. Sounds pretty reasonable, I'm just mad. Okay. So here's. Imagine this is like the whole thing, and imagine this goes forever, right? And this goes forever, and this goes forever. And now you're just going to draw a line here. And that line is usually the Earth-air interface. So we're kind of represent, like, everything above it is going to be 0, and everything below is going to be a constant. It's uniform. So this is now all the same stuff. Okay, so it's just like I have just half of the whole universe, and everything down below me has got some number, and everything up top is 0.
Okay, so is it safe to say it's a simplified model of
The Earth?
the Earth?
Yeah,
Okay.
that's a really good way. So, I mean, very often, we're kind of wondering, we do an experiment outside, and like, okay, we don't care about the buildings and that, so we'll just assume that the Earth is just flat. The Earth is flat, and there's nothing above it, and there's completely uniform below. But because it extends out so far as how we're thinking about mathematics, we call it a half space. But a uniform Earth with an upper layer is definitely a good point. Okay, so we've got things that kind of come down like this. And so if I'm sitting out here, I could get an electric potential V, but I've also got this formula here, right? And I can rearrange that formula, right? So right now it says, oh, the potential V is equal to resistivity times the current 2 pi R. I took this and I rearranged this, like solve for rho, is 2 pi R times V over I. Then I would actually get the resistivity of this uniform Earth. Okay, so think about that. Now this is actually kind of cool, right? Because suppose that you really were in a situation that the Earth was just really uniform. Okay? And then somebody says, well, how could you get the resistivity out? I mean, you could take a chunk, bring it to the lab, do the measurements. Okay, that's option one. But the other is like, okay, why don't I do something different? Why don't I take that circuit? I'm just going to put a current in, boom, and then just measure the electric potential. And then I've got a formula that tells me what this is. So it's as simple as that. That's the basic. I want to know what the resistivity is. Let me put in a current, measure the electric potential, and use this formula. I'm good to go. Okay? Now you guys are all engineers. So if I asked you to do this, okay, so now we've got physical understanding. Okay, we want to take something, just put a current in, okay, and then I measure the potential. Can you, as engineers, build a system that does that? Who's the smartest engineer here? Oh yeah, okay, so go ahead. People were pointing. No, I do agree. No. people were pointing to you. I came from both sides, so I assume that must be true. Yeah, okay. So the question is, like, as a physicist, like, I come along and I say, oh, this should be really easy. I just have to put a current into the ground, okay? I just do that. I'm going to take a stake, put a current into the ground, and I'm going to measure the electric potential up here. Can I do that? Can you do that? Okay, so what? Okay, so good. Okay, so how are you going to do that? No, this is actually good. Okay, so let's just think about the first one. How are you going to put a current into the ground? Okay, you got a battery, good. And what do? Perfect. So we got a battery. Okay, so here's our battery, right? And it's got a plus. Okay, so I mean presumably you're going to run a stake here, right? Put a steel stake, and you're going to run a current here, or run a wire. Okay. Okay, is that going to work?
Don't you need a negative sign for it to like flow to?
A gold star. Oh. Whoa! Whoa! Yes. You can't take. You can try it. Take a battery, hook a wire up to it, put one end to an electrode, plug it around, and see how much current is flowing through. You put a little ammeter in. That works. Because you need to have two amps. So I need another amp. So we're going to call this the A electrode, and the negative amp we're going to call the B electrode. So if I'm going to put any current into the ground, I need to have two grounding points so that I get a circuit, right? So now I've got a circuit, right? Because I've got a current in here, and there's something happening here. I'm pulling the current out here, and I've got myself a circuit. Okay, so what is that going to do? Let's suppose I have this. So I put a current in here and a negative current in here. What do you think the electric potential is going to be at the surface? Well, what about over here? Yeah. Yeah, so and remember I said a battery is just like putting a big charge and then they'll get this current. So the electric potential here kind of forget about this, right? We're close to this electrode, it's kind of going to go like that, right? Right. Let's assume that B is a little ways away. What's B? What's the potential going to be like at B? Pardon me?
Negative.
Negative, right. Yes, it's like in one case I've got a positive charge, so it goes up like this, and negative charge comes in like this. Negative charge here, so this potential is going to kind of go like that. So it's going to be, here's my potential if I drew it on the surface, the infinitely positive electrode, infinitely negative here. Okay, so that's what's going to happen to the potential. Now let's come together part of the experiment. Can I measure the electric potential? Can I measure electric potential? Right? Well, exactly. Okay, so now, perfect. What do we do with the voltmeter? How are we going to do that? Right? And how many ends of a voltmeter do you have?
2.
Ah, right. So we can't measure the voltage. Okay, we can measure voltage difference. That's really the only thing. That's the only thing we can ever measure is a voltage difference from something. So we could measure the voltage difference by having an electrode. Let's say M would be connected to the positive end of my voltmeter and M to the negative. So I've got a voltmeter here. So how do we put all this together in our experiment? Because now the experiment is going to be one of that looks something like this. So let's just kind of take this through. So I put in a current here. I take out a current here. And now the current lines, you can see, are, they're distorted. So around here, they're kind of radially outward, but they all eventually flow from the A electrode to the B electrode. So you can see how they flow. My electric potential is now kind of what we just sketched out on that board. My experiment is this. I have 4 electrodes. I got 2 current electrodes, a positive and a negative, and I got 2 potential electrodes, a positive and a negative. And I want to compute somehow what that electric potential difference is here when I've got this system. And what we're going to make use of is the principle of superposition. In other words, if I'm at some point here, Vm, so if I'm at some point over here, then I can measure, let's have the distances RA, and so we'll use the subscripts here to tell us the distances. So my potential is going to be whatever I have here. So the current varies as 1 upon RAM. So I do rho naught I over 2 pi r. So that's going to be from here. But then I've got a negative potential from here, from unit B, of whatever this distance is. So it'd be minus 1 over R E. So we can use superposition to tell us what the voltages are here due to 2 currents. And then we're actually going to say, oh, our measurement is your delta V, which is Vm minus Vn. And so I'm going to have now my final number that I get, like so many volts, okay, is going to be dependent upon some spatial geometries of where my potential and current electrodes are. And that will then tell us how we actually, in practice, can find out what the electrical resistivity of that homogeneous circuit. So I want you to go ahead and read some of the GPG, lab on Monday is going to be kind of going through this base material, so do get up to fundamentals and pseudosections, and I'm going to try to get through all that stuff within one lecture on Monday so that you're prepared for the lab.